Matěj, the floor is yours.
Thank you. So, everyone, welcome to my talk. My name is Matěj Račinský. I worked for 4 years in Avast, but after we merged with Norton, we are called GenDigital. I've been using Python for around 7 years because I used it a lot during my master's studies of artificial intelligence on Czech Technical University. I will be talking about machine learning models, how deploying these models differs from deploying your regular web applications, what is similar there, what is different, and our stories in Avast and now Gen, where we deployed some machine learning models in Julia, and then we moved to TensorFlow and C++, and because language models are a thing, we are deploying also language models. I will put the slides somewhere. There will be some code, some links in the notes, so then you could go through them in your own pace after the conference is over. So what the models are about? Usually when you serve some machine learning model, the workflow is, the life cycle of the request is simpler than with the web app. You usually don't have any database. Maybe you have some feature store from which you pull the features, but usually you get your request, you pre-process the data or download some additional data, you run the actual ML model inference, then you might want to post-process the data and return the response, which is nice. It might recall you, for example, like stateless cloud functions, lambdas, cloud runs. And compared to these, it has larger artifacts because the ML models are now usually neural networks and there is lots of weights. For example, we are using some small language models which have around 82 million weights, so that's like over 300 megabytes, so you have like bigger artifacts you need to deploy and execute. It's compute demanding because you need lots of CPU power to crunch the data, and if you're using neural networks or some similar stuff, you have matrices, and to multiply those matrices you want GPU, so then you need to deploy on GPU and deal with the CUDA drivers and other stuff. And if you write your serving code well, you don't change the serving code much, so it's just living there for years. But because of concept drift and other stuff, you want to retrain the model, so you are deploying newer versions of the model while the code is staying there, so you want to split the versioning of the code and of the model. Of course, you can just have the code for the inference, wrap it in the REST API, and call it a day, but then you need to do lots of stuff around if you want to really have it in production, like store and version these models, perform some monitoring, health checks, check if it's running, how long it's running, if the results are degrading or not. You want maybe some A/B testing, you want some gradual rollouts of the new versions, or you can see if it's not going haywire. You want to horizontally scale because the compute is really demanding and there is much more. You want some batch predictions and so on. So in Avast, we were a research team who was doing lots of experiments and prototyping, and we decided to do stuff in Julia. Julia is a different programming language. It looks a bit like Python, but it's faster, and it uses LLVM. And we have lots of code in Julia, so when we needed to deploy something to the production, we didn't want to rewrite everything to Python, so we decided to wrap it in the REST API and deploy it to Kubernetes cluster. Worked quite well, but we needed to program everything on our own, so we needed to pull the newer versions of models from MLflow on our own. Julia doesn't have GIL, so you can have native multithreading, which is great, but the HTTP server doesn't have support for thread pool, so we needed to implement that. Then we were struggling with some deadlocks, and we were tuning the probes for the Kubernetes because Julia has longer startup times, so the Kubernetes was sometimes killing it, so it was lots of fun. We had private registries. In Avast, we are using on-prem Artifactory, which is like artifact registry for almost everything, except of Julia, so it doesn't support Julia packages, so we needed to develop the infrastructure around this and much more. Basically, it was working, it's still running there, it's in the production for almost 3 years, but it was lots of work, and if you have experienced people in Julia, I think it's a reasonable way to do stuff. If you don't, then it's a good idea to try to rewrite it to Python or something more stable and do it yourself because it will be quicker. You can utilize the infrastructure and ecosystem. Yeah, Julia has improved since then, but I think the things that were pain points for us didn't move that much. But I'll gladly talk about it more. Last year I had talk about, like 1 hour talk just about Julia and comparing it into Python on PyData meetup. So then to something completely opposite, to something very standardized. There is KServe. Who has heard about KServe? Okay, someone, nice. So KServe is a platform for performing machine learning inference on top of Kubernetes. It's like a whole platform. It has like plugins to Kubernetes, but it's also specification, and KServe specifies how the format of request and response should look like. And it's nice that lots of different frameworks adopt this format and this specification, so then you don't have to figure out different formats. And because we also are moving from on-prem to cloud to GCP, we decided that we will not only rewrite it from Julia to Python, but we will also move from on-prem to GCP. And because we were performing lots of machine learning on JSONs, and parsing JSONs in Python is slow, we have our parsing of JSONs in C++, and which is converting it directly to NumPy matrices. And then it goes directly to the TensorFlow tensors. So we have custom C++ code, which we are calling from the Python, and it's baked into custom Keras objects, which we are using. Also, we have the JSONs stored somewhere in the buckets, so we want to download these JSONs, convert them to NumPy matrices, and perform the inference. And we want to have it like as part of the neural network, so we wrote lots of these Keras custom code. And yeah, we have this compiled C++, and we have like our private package for this, and we want to return not only the logits or the single predicted class, but to return logits, probabilities, and names of all the classes, because then it's more convenient and people don't have to compute softmax on the client. So the naive solution would be something like this: just load the model, right? Wrap it into the Flask and call it a day. Everyone can do it. It's quite easy, but then you have to do all the stuff by yourself. So we decided we have TensorFlow model. The obvious way to do serving of TensorFlow model is using TensorFlow serving. That's nice. It's high performance C++ server, but it can run only traced models. This means that if you are saving your TensorFlow model, there is parameter trace, and if you save it with tracing, it basically traces your models and stores the C++ instructions for that, and then it can, or CUDA instructions, and there it can run them. But if we have custom Keras layers, then it can't trace them, so it wasn't usable for us. And Keras saves the data, saves the model as saved model format, and traced model is also saved model format, but although it's called saved model format, it's different formats, and then when I tried to run it, it was crashing and I was getting these ugly errors. So we found out that TensorFlow serving is no for us, and then I moved to Triton, because Triton is nice, again, high performance C++ server for the inference, developed and maintained by NVIDIA, and it's cool. You can write custom Python code because it can actually run Python, and they have Docker images prepared for you, which is nice. But they have only single version of Python baked into a C++ server, and if you want different version of Python, you need to compile the C++ server by yourself. And the Docker images are quite big, which is bothersome. In Triton, if you have TensorFlow model or like ONNX or OpenVINO, it finds out the shapes of the input and output, but for other models, you need to specify the format. So I wrote that, and then this is the table with versions, and it's all Python 3.8, and we want it newer. This is how the code looks like, but we found out that if we want to use a newer pattern, we were getting errors, and I didn't want to compile the C++ server, so we decided for TorchServe. TorchServe is great, and it's for PyTorch models, but not only for them, it's Java server, and it can support arbitrary Python code. It's installable via pip, which is nice. It has API for monitoring, deploying models, and it has its own format where you wrap the model, and then you can deploy it. You just do a few steps. You install the TorchServe, wrap the model, run it, and it's that. You can specify requirements txt, so when you start the model, it installs the requirements, which is nice. It has like KServe API and its own API. And in all tutorials, they show you if you want to write custom Python code, you need to extend the base handler, but the base handler imports torch, which you don't want for TensorFlow models, but you don't need to do this. You just implement handle method, and it will work just as fine without PyTorch. That is great. So we are serving these TensorFlow models using TorchServe. And we are using Vertex AI, which is the bunch of services in GCP for AI. It has model registry when you register the models, has endpoints where you can perform the inference, and this is how it looks like. If the model is deployed, there is UI for trying it out, and this is how the results look like, and they add for you like the model name, model version, so you know which kind of model deployed that. It's more expensive than just running VMs because you pay for the service on top of these VMs. And because I watch anime, I used Vegeta to stress test this because I wanted to see how it performs. And one replica could handle 13 requests per second, but yeah, the times were around 12 seconds for the inference, which was not that great, but it was enough for us. And Vertex AI gives you all these nice charts out of the box, which is cool. So that was nice. It's somewhat working, and then we have the language models. In the language models, it's all PyTorch because PyTorch is cool now, and it's not only PyTorch, it's also Huggingface tokenizer because you need to tokenize the text and then to feed it into the PyTorch model, and the tokenizer is written in Rust because then it's fast, and we wanted to do something quickly iterate, and you can see it's like 300 megabytes on GPU. So we decided maybe let's not bother ourselves with these complicated servers. Let's try it in the FastAPI, and then we'll rewrite it to something else. It will be too slow. So we started with FastAPI. It's nice, it's easy. You just have some health probe, predict probe. It's just a few lines of code, and it just works, and it's nice. And if you deploy model to Vertex AI, you specify the Docker image and the path to the artifact on GCS in a bucket somewhere, and path to that artifact appears in this environment variable. So I just copy it to local drive inside the Docker container when it's running, and then we run this code. It works. You get the predictions. That's nice. And this is how it looks like. Of course, you don't want to run Python code itself. You want to run it in gunicorn because that's specialized for production. And this is the configuration we use. We use multiple workers, so single container can handle multiple requests at a time, and we actually utilize the GPU. And we don't preload it. You might have noticed that it's all async, which is cool, but this heavy lifting, which actually runs the code on GPU, doesn't have async. So then it's kind of slow. So you want to do your own thread pool executor and run async IO wait for, run in executor. So then there is the main event loop, which processes the request, and then the separate thread pool executor, which processes the heavy payload. So the inference on GPU doesn't block your main loop, doesn't block other requests, health probes, and that's nice, and you can play with the amount of workers. So then you can tune it and actually utilize it much better. Of course, the base idea, simple idea you might have to optimize the code and utilize all the compute you have is to have multiple workers, and then these multiple workers will be sharing the same model, so it's not having to be loaded multiple times because the multiple workers in Unicorn are multiple processes. But if you want to share this model between multiple processes, you need to have the data in shared memory. Shared memory is on this path on Linux, but unfortunately, in Vertex AI endpoint, it's only 64 megabytes and it can't be configured. If you write to GCP support, then can raise it for the whole project, but you can't select it for individual payloads, which is annoying. But because this model is slow, every worker just loads its own model. So then we use this all to deploy it, and then I stress test that. And here we can see comparison of CPU and GPU, and this is 16 cores, 8 cores, 4 cores, 2 cores, 4 cores, 8 cores with Tesla T4 GPU. And Tesla T4 is great, it's quite cheap, so here you can see it almost single replica. You can see that Tesla with 2 cores was cheaper than 16 cores, and it handled much more requests. It was 16 requests per second, and the median times were nice, the mean latency was also nice, and the CPU models just weren't able to handle this load. And this is the, where I have, yeah, the GPU utilization in peak was like not even 10%, so these just didn't even choke. And the Vertex AI gives you all these nice dashboards, so you can see how I was ramping the amount of requests when I was trying it, and we can see that the auto-scaling kicked at the end of the benchmark, and here is the GPU utilization. And I found a weird thing, even in these small replicas or small instances which have like 3.6 gigs and 1.8 gigs, the memory utilization was showing me over 4 gigabytes, so that was weird. I thought maybe they are adding the RAM and VRAM or something like this. So I wrote a ticket to GCP, and they told me that the monitoring is perfectly okay, but there is something different. They have like internal scheduler, which figures out like where it should deploy, although you specify which type of VM you need to use. The scheduler figured out that it maybe needs more RAM than we configured, so it internally deploys to different kind of VM which has more RAM, so we get some more RAM for free, but we don't know where it's deployed, like how many RAM we have available. So it's hard to monitor this on like out of memory errors because you don't know how to set the thresholds. You need to set the alerting on a specific amount of memory. You just can't have it as a percentage from the total. So yeah, that was something interesting. So yeah, we are using this, it's working, but we just hope that we won't run out of memory. And if you deploy these models to Vertex AI endpoint, it's hard to like debug them because you can't SSH into these VMs, but you have the predict function. So you can write your own reverse shell and then execute arbitrary code. So this is my FastAPI server for reverse shell. So if I write Python Python code or shell shell code, then I execute it and I print or I grab all the output and return it as a response so I can debug it. It was really useful when I was digging into some CUDA stuff because even if it's in the Docker image, it's behaving a bit differently than on some other machines where there is CUDA. So I was digging into it and it looks like this. You need to call raw predict. The Vertex AI has predict and raw predict. Predict, they all go to the same function here, but predict performs some validation of the format and raw predict doesn't, so then you can put arbitrary stuff here, just raw text, and then it performed the code, and then I was able to debug all that. And with shell, it was working nice. I found out what I need to adjust, that I need to use the NVIDIA-based Docker image, but uninstall kubla's Python package, and then the GPU was working because there are some glitches when you install PyTorch with GPU support into the Docker image that already has NVIDIA drivers, because then it's somewhat clashing. Yeah, so in summary, we started with Julia and then moved to something more production ready. And we found out that FastAPI is really quite good for lots of cases, and the Vertex AI then provides you some nice features on top of it. But we are tied to GCP now, so like you could use MLflow, but you can't deploy models directly from MLflow because all the models must go through the model registry in Vertex AI, and everything needs Docker image. So if you want to change Docker image for the same version of the model, you need to deploy a new version of the model. And I would say just be creative and try stuff out of the box, out of the documentation they provide you, because you find out lots of interesting stuff that you can do with the software that no one tells you in the documentation. Of course, this is not end of our journey. We plan to do some proper CI/CD so we can deploy from TeamCity. We plan to serve some large language models, but researchers are still experimenting with it. And yeah, thanks for your attention, and any questions?
And may I just remind you that you can ask questions in Slido. I did not see questions in Slido right now, so please just raise your hand if you have a question.
Hello. Probably just a clarification. So you have FastAPI as a main page, yeah? And then people can ask for predict something. There is an endpoint for predicting, and you're predicting calculation on spot without any saving any data anywhere.
Yeah, we're like, this is for our internal services, so our other internal services are querying this endpoint because we have like micro-service architecture. And we are, yeah, for some stuff, we are logging the request and response, and I think and then it depends on the use case, what is the retention time of the logs. Okay. And some of the data is PII, and in some use cases, the data is PII stripped, so we already train on PII stripped data, and the PII data is stripped in the request itself, so we don't get PII data.
The versioning of the models is taken care of by TensorFlow somehow.
Versioning of the models is just done by Vertex AI or by ourselves. That if we have newer version of the model, then we register that version as a new version of the model in Vertex AI model registry, and then we deploy it as a new version. So then you have lots of these versions in the registry. So like for some products, we have like version 20 or something like this now.
Okay, thank you.
One question from Slido. Why do you have such needs for high performance?
Because you don't want to waste the performance on like HTTP overhead itself, and you want to like utilize it for the inference itself. Because we knew that the inference with downloading the payload from the bucket is slow enough itself, and we wanted to see where can we cut off the like other boilerplate code, or we know that it's faster server in C++ than in Python, so we wanted to get rid of everything that we could, because we know that there is something where we can't save the time.
Thank you for the call, first of all. Talking about speed and costs. Have you ever faced the problem about like having batch requests? So the optimal solution would be like having a batch endpoint, but it's something that you have to develop differently from a stream endpoint.
Yeah, that's what I haven't mentioned. It all is batch endpoint, because as you have the format of the data, in the KServe specification, the request is actually list of samples. So the request is instances, dictionary with instances, dot, and array. And usually for single sample, it's just single element array, but you write to the server that it assumes mini batch, so you can send like 20 or 100 these samples in single request, and then we can perform with ED inference batch-wise, and we actually do, here you can see there is a batch size 20, so this is the maximum batch size that the classifier uses. Usually just gets single sample, but it can, if you send them 20 samples, it will perform the inference on 20 samples at once and return these 20 samples. And TorchServe can actually batch also these requests. So if you can configure the TorchServe that that if 2 requests arrive within some time, like may it be like 5 milliseconds or half a second, it will wait and join these 2 requests, and your custom handler will obtain a list of requests. You can process them in a batch manner and then return a list of 2 responses, and the HTTP server will send it as a 2 responses. So then you can play with it for how much time it should wait for another request and how much requests maximum can it handle.
I see, thank you. Another question, if I can. Super. In case the inference can take, let's say, 8 hours, and you know that you will receive a request that the model will take 8 hours to respond to the user. Have you ever tried like to don't make the user wait for the call, but rather like write the data in some place and the user can take the data from there?
We didn't, like asynchronous request. We didn't have use case for this, so like it's perfectly possible. Then it would be some PubSub, right? And it would be like PubSub consumer, but we didn't have, use case for like. Actually, we have use cases when the PubSub consumer is actually running the code and then sending the data to some PubSub. So in this asynchronous manner, we have just PubSub on or RabbitMQ on top of it. So then people send messages to RabbitMQ and then they pick up the results somewhere.
Another question back here.
Thanks. I have actually 2 questions. First, how would your setup change if you would be using large language models, something bigger than you mentioned? And second, why are you using GCP and not AWS?
So great question, but not for me with the GCP because I wasn't the one doing budgeting and deals. What I've heard is that AWS didn't give us any like nice discount, but GCP did, and that happened to more companies that if you're reasonably large, you're too small for AWS, but big enough for GCP to offer you some discounts. So we have some discounts on some kind of payloads. And regarding the large language models, so we experimented with the Hugging Face text generation inference, and I saw that VLLM is much faster, that they are like 2 times faster even after the Hugging Face text generation inference implemented the paged attention. They are still faster, so we will probably want to use this. It will be a bit more complex setup because then you need to share the model. Here we didn't have to share the models, so it will be more interesting. And FastAPI will probably not be enough. Even the TorchServe might be tricky. So there we probably want to just deploy the VLLM or something similar.